Now for some discussion about topics from Chapter 4, starting from the beginning, where we'll have to describe the difference between covalent bonds and ionic bonds and how binary molecular compounds are formed from their elements. There's two definitions at the beginning of the chapter that are helpful to keep in focus as this discussion begins. And one of them is the definition of the covalent bond. The covalent bond is the bond that you get from sharing a pair of electrons between atoms. You may have seen this cartoon before. The sharing of electrons between the atoms is like glue that holds the atoms together. And in this context, it's between two unknown atoms, but they look like they're happily holding on to their electrons, sharing them. And so shared pairs of electrons is the thought we want to hang on to. A molecule, then, is that unit of matter that's held together by covalent bonds. We think of ionic compounds, and not always are we describing them carefully. They're not truly molecules, because molecules are those which are held together by covalent bonds. So that's what we're going to be working on in this chapter. The place to begin is to realize that ionic compounds are going to be very different from the molecular compounds or covalent compounds of this chapter. The ionic compounds were covered in the previous chapter. The general properties and generalizations that are shown here are really good ones to think about. There's two simple compounds, one of sodium chloride and the other being HCl, hydrogen chloride, and they have very different appearances. The sodium chloride is definitely a solid. The HCl is a gas, something else altogether. The type of bond holding them together is noted there. So ionic bonds hold together anything with sodium and chloride, metal cation, chloride anion. And the HCl is a covalent molecule between two nonmetals. But the key thing to notice is especially the melting points. We don't even have to go to the boiling points, but the melting points are drastically different. Very, very much higher for ionic compounds compared to covalent compounds because of the strength of attractions between each of the ions in an ionic solid. Another way of thinking about that is to look at representations here. So every sodium ion is surrounded on all sides by chloride ions in a crystal and in three-dimensional space. And every chloride ion is surrounded on all sides by sodium ions in three-dimensional space. And you can think of 6 sides like a cube all the way around this. Boy, that tool isn't cooperating today, sorry. And so on all sides, there's lots of strong attractions that would have to be broken before the compound could be melted. Conversely, the HCl, which is shown on the left, the HCl has individual molecules in discrete pairs of atoms combined as a molecule, and the attractions between them are far different, much, much weaker. And so the weaker attractions result in lower melting points, boiling points too. So those are important distinctions to recall as we progress along in these topics. So, I've forgotten to get the decorations out of the way for you. Let me fix that. So the way we think about these compounds is definitely that the sodium chloride is the ionic bond where the electrons are taken, not shared, and resulting in ions with very strong attractions between them. And by contrast, the HCl is a covalent compound, so don't be ionic, be covalent, suggesting that we should be sharing electrons between molecules. All right, so that one presumes to be HF, but it doesn't matter. It's the same idea. Another example of an ionic compound where the electrons are taken, not shared, is shown in this funny cartoon where we have cesium losing an electron to fluorine. Fluorine's grabbing an electron from it, and you get an ionic bond between the two.